Hello, welcome friends. Welcome to DLTGH. Today we are going to take the chapter Light, Reflection and Refraction. Introduction. Optics is the study of behavior and properties of light. An object reflects light that falls on it. Eyes receive the reflected light and thus we see that object. We see through a transparent medium as light is transmitted to it. Light seems to travel in straight lines. A small source of light casts a sharp shadow on an opaque object. It is usually indicated as a ray of light. If there is a very small opaque object on the path of light, it shows a tendency to bend around it. This effect is called the diffraction. Here, the straight line concept fails. Such phenomena can be explained by considering light as a wave, but wave theory often became inadequate for treatment of interaction of light with matter, and light often behaves like a stream of particles. Quantum theory says that light is neither a wave nor a particle. It reconciles the particle properties with the wave nature. Reflection of light. Laws of reflection of light. Angle of incidence is equal to the angle of reflection. The incident ray, the normal ray to the mirror at the point of incidence, and the reflected ray all lie in same plane. These laws are applicable to all types of reflecting surfaces, including spherical surfaces. A highly polished surface, such as a mirror, reflects most of the light falling on it. Images formed by plane mirror is virtual and erect. The size of an image is equal to that of the object. The image formed is as far as behind the mirror as the object is in front of it. Further, the image is laterally inverted. Reflection of light. The formation by curved mirror. Consider the curved surface of a shining spoon is a curved mirror. The image at its concave side is real, inverted and diminished. If the spoon is moved away, image becomes smaller. Image at the convex side is virtual, erect and diminished. If the spoon is moved away, image becomes smaller. The most common used type of curved mirror is a spherical mirror. Spherical mirrors. There are the mirrors. Spherical is the reflecting surface of two types, concave mirror and convex mirror. Concave mirror is reflecting surface is curved inwards, faces towards the center of sphere. In convex mirror, its reflecting surface is curved outwards. Spherical mirrors in that four parts are there: poles, center of curvature, radius of curvature, principal axis. It is a pole is a center of reflecting surface of a spherical mirror. Reflecting surface is a part of sphere. Center of curvature. It is a center of sphere of which the spherical mirror is a part. It is not the part of mirror and lies outside reflecting surface. It lies in front of concave mirror and behind a convex mirror. Radius of curvature. It's a radius of sphere of which the mirror forms part. The distance PC equal to radius of curvature. Principal axis. It is an imaginary straight line passing through the pole and center of curvature of a spherical mirror. It is normally to the mirror at its pole. Principal focus F and focal length small letter f. Direct the reflecting surface of a concave mirror towards the sun and direct the reflected light onto a paper. Move the paper to find a bright sharp spot of light on it. Wait for a few minutes. The paper burns and catches fire. This is because the light from the sun is concentrated at a point of paper as a bright spot. Image of the sun. This point is the focus of concave mirror. It produces heat and ignites the paper. Distance of this image from the position of the mirror is the focal length of the mirror. This can be represented as ray diagram. When several rays parallel to the principal axis fall on a concave mirror, the reflected rays meet or intersect at a point of principal axis of the mirror. This point is called principal focus of the concave mirror. In convex mirror, the reflected rays appear to come from a point on the principal axis. This point is called the principal focus of the convex mirror. Distance between the pole and the principal focus of a spherical mirror is called the focal length. The reflecting surface of the spherical mirror is generally spherical and has a circular outline. The diameter of the reflecting surface is called aperture. The distance Mn. We consider only spherical mirrors whose aperture is smaller than its radius of curvature. For spherical mirrors or small apertures, the radius of curvature is equal to twice the focal length, r equal to 2f. Principal focus lies midway between the pole and center of curvature. Image formation by spherical mirrors. Activity. Find out approximate focal length of a concave mirror. Mark three parallel lines P, F and C on a table such that the distance between any two successive lines is equal to the focal length of the mirror. Place a stand with a concave mirror over the line P such that its pole lies over the line. Keep a bright object, burning candle, at a position far beyond C. Place a paper screen and move it in front of the mirror to obtain a sharp bright image of the candle flame. Repeat the activity by placing the candle A. Just beyond C, B. At C, C. Between F and C, D. At F, E. Between P and F. Nature, position and size of the image formed by a concave mirror depends on the position of the object in relation to P, F and C. Representation of images formed by spherical mirrors using ray diagrams. In an extending object, each small portion acts like a point source. An infinite number of rays originate from each point, but it is easier to consider only two rays. For clarity of the ray diagram and to know their directions after reflection, the intersection of at least two reflected rays gives the position of the image of the point object. Any two of the following rays can be considered to locate the image. A. A ray parallel to the principal axis, a ray through the principal axis of a concave mirror or towards the principal focus of a convex mirror. A ray through the center of curvature of a concave mirror or directed in the direction of the center of curvature of a convex mirror. A ray incident obliquely to the principal axis towards pole P. A ray parallel to the principal axis after reflection, it passes through the principal focus in concave mirror or appear to diverge from principal focus in a convex mirror. A ray through principal focus of a concave mirror directed towards the principal focus of a convex mirror, after reflection, it emerges parallel to the principal axis. A ray through the center of curvature of a concave mirror or directed in the direction center of the curvature of a convex mirror, then it's reflected back along the same path because the incident ray falls on the mirror along the normal to the reflecting surface. A ray incident obliquely to the principal axis towards pole P on the concave mirror or a convex mirror, it is reflected obliquely. In all these cases, the laws of reflection are followed. Angular reflection equal to the angle of incidence. Image formation by the concave mirror. Position of the object, position of the image, size of the image, nature of image. At infinity, the position of the image will be at focus, size of the image will be highly diminished, point size, and the nature will be real and inverted. When it is beyond C, it will be between focus and center of curvature. The size will be diminished and real and inverted. At center, the position of the image will be at center itself and same size, real and inverted. Between C and F, beyond C, enlarged, real and inverted. At F, at infinity, highly enlarged, real and inverted. Between P and F, behind the mirror, enlarged, virtual and erect. When the object between F and P, image is not appearing on the screen. Here, virtual image can be seen in the mirror. Use of concave mirrors. Use a torch, searchlight and vehicle's headlight to get powerful parallel beam of light. Use a shaving mirrors to see a large image of the face. Used by say dentists to see large images of teeth of patients. Large concave mirrors are used to concrete sunlight to produce heat in solar furnaces. Image formation by convex mirror. Show a pencil in the upright position in front of a convex mirror. It, its image in the mirror is erect and diminished. As the pencil is moved away from the mirror, the image becomes smaller and move closer to the body, to the focus. Sorry. Image formation by a convex mirror. Two portions of the object to study the image formed by a convex mirror are shown below. The position of the object at infinity, position of the image will be at focus behind the mirror. The size will be highly diminished point size. The nature will be virtual and erect. If the position is between infinity and the pole, the position of the image will be between pole and focus behind the mirror. Size will be diminished and nature will be virtual and erect. In plane mirrors and concave mirrors of any size, we cannot see a full-length image of a distant object. But it is possible in a convex mirror with a wider field of view. A convex mirror is filled, fitted in a wall of Agra Fort facing Taj Mahal to observe the full image of Taj Mahal. Uses of convex mirrors. Convex mirrors give a erect diminished virtual image. Also, they have a wider field of view as they are curved outwards. So, they are used as rear viewing mirrors in vehicles. It enables the driver to see traffic behavior. Sign convention for reflection by spherical mirrors. New Cartesian sign convention. In this convention, the pole P of the mirror is taken as origin. The principal axis of the mirror is taken as x-axis, x dash x of the coordinate system. The new Cartesian sign of the spherical mirrors are shown in the image. The object on the left of the direction of the light will be positive. The convention are as follows. The object is always placed to the left of the mirror. Light from the object falls on the mirror from the left hand side. All distances parallel to the principal axis are measured from pole of the mirror. All distances measured to the right of the origin along x-axis are taken as positive while those measured to the left of the origin along x-axis are taken as negative. Distances measured perpendicular to and above the principal axis along plus y-axis are taken as positive. Distances measured perpendicular to and below the principal axis along minus y-axis E are taken as negative. Sign convention are applied to obtain the mirror formula and solve related numerical problems. Mirror formula and magnification. In a spherical mirror, the distance of the object from its pole is called the object distance. It is represented by the small letter u. The distance of the image from the pole of the mirror is called the image distance. It is represented by the small letter v. The distance of the principal focus from the pole is called focal length and it is represented by the small letter f. Mirror formula is 1 by v plus 1 by u gives 1 by f. This formula is valid in all situations for a spherical mirror for all positions of the object. Magnification. Letter M. It is the enlargement of the image formed by spherical mirror relative to the size of the object. It is a ratio of the height of the image h dash to the height of the object h. Magnification equal to height of the image h dash by height of the object h. The magnification is also related to the object distance u and image distance v. It can be expressed as minus v by u. The height of the object is taken to be positive as the object is placed above the principal axis. The height of the object is taken as positive for virtual images and negative for real images. A negative sign is value of the magnification indicates that image is real. A positive sign that indicates the image is virtual. For part 2, we'll continue in this video itself. Let's light reflection and refraction, second part. Refraction of light. Light seems to travel along a straight line path in a transparent medium. Light does not travel in the same direction in all media. It appears that when traveling obliquely from one medium to another, the direction of propagation of light in the second medium changes. This phenomenon is called refraction of light. Refraction is varied in different media such as kerosene, turpentine, transparent plastic slab, etc. Refraction of light examples. Bottom of a tank or pond contains water appears to be raised. When a thick glass slab is placed over a printed matter, the letter appeared raised. A pencil partly immersed in a water is a glass tumbler appears to displace at the interface of air and water. A lemon kept in water in glass tumbler appears to be bigger than its actual size when viewed from the sides. Experiment 1. Place a coin at the bottom of a bucket filled with water. With our eye to a side above water, try to pick up the coin in one go. We need not succeed. Reason: the reflected light coming from the submerged coin in water, denser medium on entering air, rare medium bent away from the normal due to the refraction of light and image size becomes larger than its actual size. Thus, coin appears to be closer than its actual size. Experiment 2. Place a large shallow bowl on a table and put a coin in. Move away slowly from the bowl. Stop when the coin just appears from our sight. Ask a friend to pour water into the bowl without disturbing the coin. The coin becomes visible again. This is because the coin appears slightly raised above its actual position due to refraction of light. Experiment 3. Draw a thick straight line on a white paper. Place a glass slab over the line such that one of its edges make an angle with the line. Took Look at the portion of the line under the glass slab from the sides. The line under the glass slab appears to bend at the edges. It is due to the refraction of light. Place a glass slab normal to the line. The part of the line under the glass slab does not appear bent. It appears in a straight line because a ray of light perpendicular to the plane of refracting medium does not change its angle due to refraction. Look at the line from the top of the glass slab. Part of the line appears to be raised. This is due to the refraction of light. Fix a white paper on a drawing board and place a rectangular glass slab on its middle. Draw the outline ABCD of the slab. Fix two pins E and F vertically such that the line joining the pins is inclined to the edge AB. Look the images of the pin E and F through the opposite edge. Fix two other pins G and H such that these pins and the image of E and F lie on straight line. Remove the pins at the slab. Join the portions of the tip of the pin E and F and produce the line to B. Let's EF mean AB at O. Similarly, join the positions of tip of the pin G and H and produce it up to the edge CD. Let HG meet CD at O dash. Join O and O dash also produces EF up to P. Here, the light ray has changed its direction at O and O dash. Both the points O and O dash lies on a surface separating two transparent media. Draw a perpendicular N dash at to AB at 0 and another perpendicular M dash to CD at O dash. The light ray at point O enters from a rarer medium, air, to a denser medium, glass. The light ray bends towards the normal. At O dash, the light ray enters from the glass to air, denser medium to rarer medium. The light here bends away from the normal. Compare the angle of incidence with the angle of refraction. At both refracting surfaces AB and CD, a ray EO is obliquely incident on surface AB, called incident ray. OO dash is the refracted ray of O dash H is the emergent ray. The emergent ray is parallel to the direction of the incident ray. The extent of bending of the ray of light at the positive opposite parallel faces AB, air glass interface, and CD, glass air interface of the rectangular glass slab is equal and opposite. This is why the ray emerges parallel to the incident ray. However, the light ray is shifted sideways slightly. When a light ray is incident normally to the interface of two media, it goes along the same straight line. The refraction is due to the change in speed of light as it enters from one transparent medium to another. Laws of refraction of light. The incident ray, the refracted ray, and the normal ray, the interface of two transparent media at the point of incidence, all lie in the transparent and same plane. The ratio of sine of angle of incidence I to the sign of angle of refraction R is a constant. For the light of a given color and pair of media, this is also known as Snell's law of refraction. It is true for angles 0 and above and 90 and below. Sin I by sin R equal to constant. This constant value is called refractive index of the second medium with respect to the first. It is a ratio of the speed of the light in pair of media. It is used to measure the change in direction of a light ray occurring in two media. Light travels fastest in vacuum, 3 into 10 raised to 8 meter per second. In air, there is only marginal decrease. It reduces considerably in glass or water. Considering a ray of light traveling from medium 1 into medium 2, then the refractive index of medium 2 with respect to the medium 1 N21 is the ray of speed of light in medium 1 V1 and speed of light in medium 2 V2. Hence N21 speed of light in medium 1 by speed of light in medium 2 equal to V1 by V2. Refractive index of a medium 1 with respect of the medium 2 is represented as N12. Speed of light in medium 2 by speed of light in medium 1 equal to V2 by V1. The ratio of the speed of the light in vacuum or air, medium 1 and medium 2 is called absolute refractive index. It is represented as N2. If c is the speed of the light in air and v is the speed of the light in the medium, the refractive index of medium Nm is speed of light in air by speed of light in the medium, c by v. The absolute refractive index of a medium is simply called its refractive index. The refractive index of a water Nw equal to 1.33. For example, speed of light in air by speed of light in water gives 1.33. Refractive index of ground glass Ng equal to 1.52. Ability of medium of refraction is expressed in terms of optical density. It is not the same as mass density. An optical denser medium may not have greater mass density. Example, kerosene is optically denser than water, but its mass density is less than water. Here some of the examples are given for the material medium in refractive index, material medium and refractive index itself. The terms rarer medium and denser medium actually means optically rarer medium and optically denser medium. Medium of large refractive index is optically denser. Medium of lower refractive index is optically rare. The speed of light is higher in a rarer medium, so a ray of light traveling from a rarer medium to a denser medium slows down and bends towards a normal. When it travels from denser medium to a rarer medium, it speeds up and bends away from the normal. Refraction by spherical lenses. A transparent material bound of two surfaces on which one of both surfaces are spherical forms a lens. The glasses used in spectacles and magnifying glass used by watchmakers are examples of lenses. In a lens with only one spherical surface, the other surface would be plane. There are plano-convex, plano-concave, biconvex, biconcave, and meniscus. A lens with the two spherical surfaces bulging outwards is called double convex lens. Simply a convex lens. It is thicker at the medium than at the edges. Such lenses converge light rays, so it is also called converging lens. A double concave lens. Simply a concave lens is bounded by two spherical surfaces curved inwards. It is thicker at the edges than at the middle. Such lenses diverge light rays, so they are also called diverging lenses. A convex lens or concave lens has two spherical surfaces. Each of them forms a part of a sphere. The center of these spheres are called center of curvature of the lens, C1 and C2. An imaginary straight line passing through the centers of curvature of a lens is called its principal axis. The central point of a lens is its optical center, O. A ray of light through the optical center of a lens passes through without any deviation. The effective diameter of the circular outline or spherical lens is called its aperture. Thin lenses with small apertures, the lenses whose aperture is much smaller than its radius of curvature, and two centers of curvature are equidistant from the optical center. Incident of spiral rays on a lens. Using a convex lens, focus the light from the sun on a paper. Obtain a sharp, bright, real image of the sun. Hold the paper and lens in the same position for a while. The paper begins to burn and catches fire. The parallel rays of light from the sun are converged by the lens at the sharp, bright spot on the paper. It generates heat and causes burning of the paper. When several rays of light parallel to the principal axis fall on a convex lens, they undergo refraction from the lens and converge to a point on the principal axis. This point is called principal focus of the convex lens. When several rays of light parallel to the principal axis fall on a convex lens, they undergo refraction from the lens and diverge from a point on the principal axis. This point is called the principal focus of the concave lens. If parallel rays are passed from opposite surface of the lens, another principal focus is formed on opposite sides. A lens has two principal foci, f1 and f2. The distance of principal focus from the optical center of a lens is called focal length. The distance between the position of convex lens and position of image of the sun gives approximate focal length of the lens. Image formation by lenses. Image formation by convex lens. Take a convex lens, find its approximate focal length. Draw five parallel straight lines on a table such that the distance between the successive lines is equal to the focal length of the lens. Place the lens on the central line such that the optical center of the lens lies just over the line. The two lines on either side of the lens correspond to f and 2f of the lens respectively. Mark them 2f1, f1, f2 and 2f2 respectively. Place a burning candle far beyond 2f1 to the left. A clear sharp image is formed on a screen placed at f2. Repeat this activity by placing object just between f1 and 2f1 and at f1 between f1 and O. Nature portion are relative size of the image formed by convex lens for various portions of object at infinity at f2, highly diminished point size and real and inverted. Beyond 2f1, between f2 and 2f2, diminished, real and inverted at 2f1, at 2f2, same size, real and inverted. Between f1 and 2f1, beyond 2f2, enlarged, real and inverted. At the focus f1, at infinity, infinitely large or highly enlarged, real and inverted. Between f1 and O, on the same side of the lens as the object, enlarged, virtual and erect. Image formation by a concave lens. Place a burning candle on one side of the concave lens. Look through the lens from the other side and observe the image. Image will not be obtained on a screen but can be observed through the lens. Move the candle far away from the lens. The image becomes highly diminished. Nature portion and relative size of the image formed by a concave lens for various portions of the object. Position of the object at infinity at f1, highly diminished, point size, virtual and erect. Between infinity and 0, O, between f1 and O, diminished, virtual and erect. A concave lens always gives virtual, erect and diminished image irrespective of the position of the object. Image formation in lenses using ray diagrams. For a drawing ray diagrams in lenses, any two of the following rays are considered. A ray parallel to the principal axis after refraction from the convex lens passes through the principal focus on the other side of the lens. For a concave lens, the ray appears to diverge for the principal focus on the same side of the lens. A ray passing through a principal focus after refraction from the convex lens emerges parallel to the principal axis. A ray of light appearing to meet at the principal focus of concave lens after refraction emerges parallel to the principal axis. A ray passing through the optical nerve center, it emerges without any deviation. The ray diagrams for position, size and nature of the object formation in a convex lens for few position of object refer the table. The ray diagrams for the image in a concave lens for various positions of the object refer the table. Sign convention for spherical lenses. It is same as the sign convention used in spherical mirrors. The rules are applied for a sign or signs of distances by measurement are taken from optical center of the lens. According to the convention, focal length of convex lens is positive and that of concave lens is negative. Formula of the spherical lenses gives the relationship between object distance u, image distance v and focal length f. The lens formula is expressed as 1 by v minus 1 by u gives 1 by f. The lens formula is general and is valid in all situations for a spherical lens. The magnification M produced by lens is similar to that of spherical mirrors. It's the ratio of the height of the image h dash and height of the object h. M equal to h dash by h. Here h dash is height of the image and h is height of the object. Magnification is also related to the object distance u and the image v. Magnification m equals by h dash equal to v by v. The ability of the lens to converge or diverge light rays depends on the focal length. A convex lens of a shorter focal length bends the light rays through large centers, angles of focus closer to the optical center. The concave lens of very short focal length causes higher divergence than the one with a longer focal length. The degree of convergence of divergence of light by a lens is expressed as its power. The power of a lens P is defined as the reciprocal of the focal length. A unit of power of lens is diopter. 1 diopter is the power of a lens whose focal length is 1 meter. 1 D gives 1 meter 1 by m. The power of a convex lens is positive and that of a concave lens is negative. Power of lens. Opticians prescribe corrective lenses indicating their powers. It is more convenient to use power instead of focal length. A lens of plus 2.0D has a focal length of 0.50 mm. The lens is convex. The lens of power minus 2.5D has a focal length of minus 0.40 meter. The lens is concave. In many optical instruments, several lenses are combined to increase magnification and sharpness of the object. The net power P of the lenses placed in contact in the algebraic sum of the individual power P1, P2, P3, P equal to P1 plus P2 plus P3 like that goes. During eye testing, an optician puts several Cartier lenses of known power inside the testing spectacle frame. Thus, the required power of the lens is calculated by algebraic addition. Two lenses of power plus 2.0D and 0.25D is equivalent to single lens power 2.25D. The simple additive property of the powers of lenses can be used to design lens system to minimize certain defects in images produced by lenses. Such a lens system is commonly used in the design of lenses of camera, microscopes and telescopes. That's the end of the video. If you like the video, plus subscribe the channel, share the video with your friends, comment if you have any doubts, and like the video. Don't forget to like the video. So that's it. We will see in the next video. Till then,